Here's an introduction to the Hertzsprung-Russell diagram to accompany Chapter 18 of the textbook Astronomy from Open Stax. So what is the Hertzsprung-Russell diagram? What you basically do is you take some number of stars. For each star, you get its luminosity and you get its surface temperature, and you plot that as one data point on a graph. And then when you do this for lots and lots of stars, you get this this plot here. So temperature increases as you go towards the left. Equivalently, you could do color instead, so where the red stuff's on the right and the more blue you are is on the left. And the vertical direction is how bright an object is. And in this case, we're using intrinsic luminosity. You could use the apparent magnitude, but then you would want to make sure that all of the stars are at the same distance, or roughly the same distance, for this graph to make sense. So what we're looking at here is the HR diagram for many of the sort of nearish by stars. So you're looking at 4 million stars that are within 5 million light years, or sorry, 5,000 light years of the sun. And as we're going to see, this is a useful tool for understanding stellar evolution, for getting properties of stellar clusters. And what we're going to try to do here, though, is we're going to try to understand the pattern that we see here. Right? There's not some arbitrary distribution. We have clear patterns going on. So let's try to understand that. And one thing I do want to mention on this plot is, what does the color mean? It's intensity, so how much you have. So the yellow and orange means you have a lot of stuff. The black means you have only a little bit. So before we can understand the patterns here, we need to talk a little bit about stellar properties and how we determine those. So first, let's go into masses. So if we want to determine the mass of a star, one of the best ways to do it, if you can get a good spectrum, is to use the spectral lines if it's in a binary star system. So at least half of all stars are in a binary star system, and so this isn't as niche of a method as you might think it would be. What you basically do is you point your telescope at two stars. You don't necessarily even need to be able to visually separate them for this. And so you're looking at the two stars, and you find some spectral line that they have in common. So this could be some calcium line, for instance. And you observe these two lines over time, so over a matter of days, or maybe even hours, and you're watching how the relative wavelength of these two shifts. So you have the two stars, for instance, in this position. Star A is coming straight at you. Star B is moving far away. So the spectral line for A is going to be blue shifted. For B is going to be red shifted. When the two stars are moving perpendicular to us, there's no red shift or blue shift, so the spectral line is just at its kind of natural location. Then as the stars keep orbiting each other, when A is moving away, it's now red shifted, and B is moving towards us, it's now blue shifted, and so on. And this pattern repeats. And you can use this to determine the radial velocity, which is the vertical direction, over time of these two objects. So we can see, blue moving towards us and then away from us, and so on. So how do we actually get masses from this? Well, we need to use Kepler's third law. So remember what Kepler's third law is that the semi-major axis, which is sort of like it'd be the radius if it was a circular orbit, the semi-major axis cubed is proportional to the period squared. And if we're using astronomical units for the semi-major axis, so this is astronomical units is 1 is an Earth to Sun distance. If you're using the sum of the two masses of the stars in solar masses, and then the period in years, then this proportionality becomes an equality directly. And so the semi-major axis cubed is equal to the sum of the masses of the two stars times the period of the orbit squared. And the semi-major axis, if this is a visual binary, we can get this directly by just measuring the distance from the focus of this ellipse to our star. And the period we get from basically mapping this wavelength shift over time. So the period is defined as when you have a wave-like cycle is from one crest to another. So that's just that time. So in this case, our period would be something like 17 days or so, right? Because you peak it around 21 and you peak it around 4, so something like 21 days is the period in this case. And so great, that gives us the sum of the masses. If we want to get individual masses, we need to get relative velocities. And connecting that to the individual masses takes a little bit of extra physics. You basically have to take an undergraduate course in classical mechanics. If you do that, then you can go ahead and work out those. But it's relatively straightforward. We're just not going to do it here because it's slightly beyond the introductory level. If you want to understand it in a qualitative sense, you can look at this relative velocity versus time. You'll notice that one of these objects here, star A, is not changing all that much. Star B that is changing quite a bit. And so what would this mean? It would mean that star A is closer to the focus. It's basically it's closer to the focus, so it must be the higher mass star. Star B is further away. It must be the lower mass star, and you can think of this kind of like two objects on a fulcrum. So you can interpret these patterns to get information about the relative masses of the two of these. One issue is that the orbital inclination is also going to impact this result. So in the example here, we're basically acting as if the observer is kind of down here looking towards the star, these two stars, but you could be at different angles relative to this plane of the orbit, so it's sometimes only going to give you a limit on masses. So that's one issue. The best way to get high precision masses is to get lucky and to have an eclipsing binary system. So in an eclipsing binary system, you basically are lucky enough that the orbit of the two stars, you're viewing that edge on, and so you now know the orbital inclination. And you can look at the light of these two coming from these two stars, and you'll see when you're basically hiding the little star in this case, the light curve goes down, there's less light that you can see. And then also when the little star passes in front of the big star, it blocks out some of that light. And so again, there's a dip, but it's a smaller one in this case. And the exact pattern that you get here is going to depend on the inclination angle, so whether it's at a partial eclipse or a full eclipse, but you can interpret that angle from the pattern, which is pretty cool. And then also it's going to depend on the relative sizes of the two stars. So in this case, we have one that's clearly smaller than another. If instead the two objects are very comparable to each other, then you might get a pattern like this, where you still have one of these dips is one star eclipsing the other, and then the second, one star going behind one, and then going in front of the other. But in this case, because they're comparable, the two dips look kind of similar. If you want a real case that's more like this cartoon that's shown here on the left, then you'd get something like this, where you have a deeper dip and then a slightly shallower dip. And so this is going to be your little star being hidden behind the big star, and then the little star coming in front of the big star. Okay, so what do we learn from measuring all those masses? Well, we can figure out what the mass distribution of stars is, just in the local universe where we can get these masses. And we can plot that as a distribution. Technically, we're mostly interested in the mass distribution of stars at their birth. Mass loss does occur, but most stars, are not that different in mass from the mass they were born with. And you can plot that, so you have something that's basically the number of stars in the vertical direction. That's a little more complicated than that. Roughly the number of stars versus their mass at their birth. And you see that actually most stars are less than a solar mass. So this vertical black line, this is the mass of our sun. And stars that are higher mass are just more and more rare. This is a logarithmic scale, so ones that are 10 solar masses are exceedingly rare relative to 1 solar mass. And it's much more common to have something that's like a tenth of a solar mass. As you can see, there are different theoretical predictions here, so it's not all totally certain, but things are kind of converging into this distribution here between this purple, cyan, and red. So you have a similar likelihood of things that are around, 0.5-ish or 0.2-ish maybe to 100th of a solar mass, and then it drops off rapidly afterwards. So clearly, most stars are actually lower mass than the sun. Now, we want to be able to say something about the HR diagram, right? That's what this little presentation is about. But that HR diagram just had luminosity versus temperature. So we need to, let's see if we can link mass to luminosity and then somehow gain a better understanding of what we're seeing in our HR diagram. So it turns out if you just go ahead and take stars and you plot their luminosity versus their mass, and in this case you have log scale, you get a very clear relationship, right? So this is 80 years ago that this was observed, but you have a very clear pattern. It's not a random scatter at all. And it turns out if you do this for lots of stars, and you can see, and even he knew 80 years ago, that the luminosity is roughly the mass to the 4th power, it turns out. You can explain this with stellar structure, but we need more advanced knowledge than we're going to go over in this introductory course. So take an upper level astrophysics class and you can understand this. But in any case, the mass and the luminosity are directly linked. Now this is true for most stars, for 90% of stars. When a star does not follow this pattern, that means there's something interesting about that star. It must be a little bit different than the 90% of those other stars. So if we go ahead and plot mass on the Hertzsprung-Russell diagram, we can do this for the stars. We relate our mass to our luminosity, and you just get a couple of example points here. So a 10 solar mass star would be along this diagonal band, would be up here near the tip of where we observe nearby stars. Something that's similar to our sun, 1 solar mass, would be right where the bright part begins. And then down here, a tenth of a solar mass is down kind of at the tail end of this main distribution of stars. So this is where we can kind of make sense of where the bright pattern is and where it's dim otherwise. Right? We said the initial mass function basically only increases after 1 solar mass when you get lighter. And that's why most of the stars, most of the intensity, are concentrated down in this low mass region, because that's how most stars are born. So we've already kind of understood this. One thing that I didn't prove to you, but I can tell you, is that if you take the mass-luminosity relationship and you look at stars that are on this diagonal band, they follow that luminosity goes as mass to the 4th very well. The stars that are off the diagonal band, these do not. And we'll learn later in stellar evolution, when we discuss that this main diagonal band is called the main sequence. These stars are converting hydrogen to helium in their core, and the other stars, these are not. These are at different stages of their stellar lifetime that we'll get to in another lecture. Okay, so what about radii? Maybe we can learn something about stars in the main sequence when we consider radii, or not in the main sequence, sorry, just in the Hertzsprung-Russell diagram. So how do we get stellar radii? One way to do it is from the flux. So we talked about this in the Introduction to Light lecture. We can approximate our star as a black body, which is, usually an okay approximation, if not a great one. And what that means is that the luminosity of a star is proportional to the radius squared times the effective temperature to the 4th power. And so if you have a greater luminosity but the same effective temperature, then that means that star has a larger radius. Or if you can get the 2 effective temperatures and get the 2 luminosities, then you can relate the 2 radii to each other. When you go ahead and do this, you can get this this particular plot. You have the log of the radius, so this is log scale, versus your temperature sequence. So remember, the cool stars are down here, the hot ones are here. And while in the mass
diagram, this was a couple orders of magnitude in mass. You see here, you mostly just have kind of a factor of a few difference in the radius. So the stellar radii along the main sequence are not all that different, just what we observe. Now, there's a couple issues with this method, is that you need to be able to see the stars separately to do this. And the temperature and the luminosity are often not determined that accurately. And the black body approximation isn't always great. It's especially difficult to use when you get these cooler stars that have lots of deep spectral lines. So this particular method, has an accuracy of like tens of %. So it's pretty good, but it's not great. For very high precision constraints on stellar radii, you use eclipsing binary systems. So what you have is, let's just for this extreme case here, you have a little star that is orbiting a bigger star. Now really they're both orbiting each other, okay? But if one of them is a lot bigger than the other one, then the focus of their orbits is going to be somewhere inside the big one. So let's just go with this cartoon. So we have our little star, we can see it, it goes behind the big star, it emerges again, comes in front of it, and then is off to the side and repeats. So that's what we're going to go with. So what would that look like on our brightness versus time plot that we have here? What I've done is I've mapped the points of the light curve to points in the orbits here. So 1, our little star is just about to go behind the big one. At 2, the little star has just now gone completely behind the big one. At 3, the little star is just about to emerge. And at 4, it's finally emerged again. Then our little star is going to go in front of the big one and block some of its light. And you'll repeat this process, but you'll have a slightly shallower dip, or a lot shallower, depending on the relative size of these two objects. So how do you get the radius from this? Well, keep in mind, right, velocity is defined as the distance over the time. And so therefore a distance is equal to the velocity times the time. We can just move this from the denominator over to the numerator on the other side. We can get the relative velocity from spectroscopy, as we've discussed. So you look at the redshift of lines. So you get that velocity, and you measure the times from this brightness versus time curve. So you can figure out where these, 1, 2, 3, 4 happen, for instance. The radius of the smaller star in our diagram here is just going to be 1/2 of that velocity times the time difference between 0.1 and 0.2. Right? This just is how long it takes for a star to go behind there. The factor of 1/2 is because if we just took the time difference, that would be measuring the diameter. So the factor of 1/2 gives you a radius. And then similarly, the radius for the larger star, this is just the difference between when our little star is fully hidden by the big one. You could equivalently use these ones in front, where the little star is in front of the big one. It's less common because that dip is often smaller and a little harder to interpret. So usually you'd use these 1, 2, 3, 4, but there's no reason you couldn't use the 5, 6, 7, 8 as well. So this gives extremely precise radii. We're talking percent level precision, which is pretty amazing. Okay, so let's put radius on our HR diagram. So if we go ahead and plot the radius of stars versus the temperature, temperature increases to the left. This is data from eclipsing binaries. It follows the same pattern we saw for the radius for flux, but we just have some more stars now. You see most of them fall in this region of around 1/2 to 5 or so not a huge change. And we can then do this for all stars on the HR diagram, and you see roughly the following. That radius essentially increases diagonally as you increase from the bottom left up to the upper right. That radius is increasing. So most of the stars on the main sequence, these are somewhere around a solar radius. They're pretty much all bounded by 0.1 to 10 solar radii, so not a huge change in radius necessarily. And it just increases as you go further up. This explains some of the names we're going to give to regions in the HR diagram. So up here, these stars are called giants, and that's because they're giant compared to the ones on the main sequence. The stars that are down here, these are called dwarfs, and that's because they are small in size compared to the stars on the main sequence. So now we understand the HR diagram, kind of what we're looking at in terms of our stars. We'll go over the implications for stellar evolution in the future, but now let's just talk about some general stuff that we can use the HR diagram for. So one thing is we can now use our HR diagram to determine the distance to objects. So if we can determine a star's spectral class, so we observe spectral lines. Based on those absorption lines, we can figure out its temperature, or we can just determine the color. We'll get the class of the star. Then we know where it's going to be located on the HR diagram, on the main sequence. You can, for instance, if you observe a star like the sun, say, okay, it's a G star, you know that it's at this location here on the HR diagram. And for these stars, we know what their intrinsic luminosity is. And if you know the intrinsic luminosity, and you know the brightness that you measured, the apparent magnitude, then you can use that to get the distance. Right? And we talked about this in the Introduction to Starlight lecture. So the HR diagram can be used as a tool to measure the distance to stellar clusters. The HR diagram can also be used to determine the age for stellar clusters. So what we looked at previously is we had the main sequence just stretching up to very bright regions, but that was because we were looking at all stars in the surrounding area. If we instead look at a stellar cluster, for instance, let's look at M55 here, these stars were all born around the same time. Right? So we talked about this a bit in when we talked about galaxy formation. This star cluster, all of these stars were formed around the same time, and so the youngest stars are going to have burned through the hydrogen in their core. They are no longer going to fall along this thing called the main sequence, where hydrogen is being converted to helium. And so the highest mass stars, as we'll learn when we talk about stellar evolution, these will have burned through their hydrogen already, and the lower mass you are, the longer lived you are. And so then we can follow this HR diagram and see where the turnoff point is. That tells you how old this stellar cluster is, because we know what the age, the lifetime is of stars right at this boundary here. And we know because the turnoff is at that point, these stars are just about to run out of the hydrogen in their core, and so therefore we can tell exactly how old this stellar cluster is. So this is using the main sequence turnoff, which is pretty cool. And that is it for this introduction to the Hertzsprung-Russell diagram for Astronomy 1000.